Good morning. I'd like to thank you, all of you, to coming here. And I'd like to thank Jolesz family as well as Focus Ultrasound Foundation for the award. And I would like to thank Insight Tech for the very generous support. I would like to begin my presentation with a very brief overview of history behind acoustic neuromodulation. Back in 1958, Fry brothers in Illinois, they discovered the reversible neural suppression can be achieved by sonicating visual structures in cats. And on the other side, Gavrilov on the old Soviet Union, they created a neural sensation by sonicating auditory structures in humans. McGee et al. And Bechtold in the mid-1990s, they discovered the auditory sensation can be elicited during transcranial Doppler exam. And Bechtold discovered a reversible modulation of neuroactivity can be achieved in ex vivo rodent brain tissue. I personally believe that we are in the middle of a renaissance period of transcranial focus ultrasound. And we owe a lot of it to pioneers such as Dr. Heinonen and industry leader such as Insight Tech, where they developed a technique that allow us to place a acoustic focus accurately into the brain through the skull. So why do we need non-invasive brain neuromodulation? First of all, conventional pharmacological approaches are not region-specific. We have a couple of non-pharmacological approaches of neuromodulation, for instance, ECT, DBS, ECS. These are invasive procedures. We have direct current stimulation as well as transcranial magnetic stimulation. These non-invasive options, however, the area of modulation is quite large and they cannot reach deep brain areas. So we want both spatial specificity and the deep brain penetration, and focused ultrasound can provide a unique and exquisite solution for this. So in region-specific neuromodulation technique may provide unprecedented opportunity in neurotherapeutics, including functional brain mapping. So my journey began about 11 years ago when Dr. Jolesz and Dr. Alexander Bystrycki at UCLA encouraged me to examine if ultrasound can indeed stimulate the brain structures. And back then I had a real-time functional MRI technique that actually allowed me to examine a lot of different sonication parameters to expedite examining the effect of ultrasound on the brain. And I had to learn from the beginning all about the ultrasound from my great mentor, Dr. Nathan McDonald and Jason White. And here is the story. We conducted a couple of animal experiments, especially as you can see from the video clips. Can you advance the video on the rabbit, please? Yes, thank you. So we used about 500 to 600 kilohertz focused ultrasound that is given to the motor area of the rabbit on the left and the rats on the right. We used a single element transducer and we stimulated the motor area that corresponds to the paw movement as well as the tail movement of the rats and rabbits. And we gave a suppressive sonications delivered to the thalamic area of the rats that is given PTZ. PTZ is a potent GABA inhibitor, so therefore it elicits a seizure in a very acute fashion. And it elicits the seizure activity that are being monitored by the EEG. And we delivered a suppressive sonication to the thalamic area of the rat. And the seizure activity as well as ictal activity that are measured by the EEG started to decrease. Not immediately after the sonication, but about 10 to 20 seconds after the sonication. So sonication started about 5 seconds ago. And the seizure activity goes on for a while, but soon after, the sonication started to tame down some of the seizure activity right there. And we saw the complete disappearance of seizure activity. And of course, upon the end of the sonication, the seizure activity came back in about 2 minutes afterwards. But we've seen that effectively the suppressive sonication have some positive impact on suppressing the epilepsy. And we decided to examine the effect of sonication on stimulating cranial nerve structure in the rat. We decided to deliver excitatory sonications to the abducens nerve, which abduct the eyeball from the midline. And this is the example. We delivered 500 kilohertz sonication stimulation to the abducens nerve ipsilaterally. And you can appreciate only one eyeball start to move around, move away from the midline upon the sonication. When you stop the sonication, then the eyeball slowly moves back to the neutral position, which suggests that it has some efficacy in stimulating the cranial nerve. So motivated by the long history of small animal and large animal studies, we were motivated to study the effect of sonication in humans. And along with the collaboration with my collaborator in South Korea, we decided to deliver a stimulatory stimulations to the somatosensory area of the brain, and we elicited a tactile sensation can be felt by the subjects. And we also decided to deliver excitatory sonications to the visual area of the human brain, now under the monitoring of fMRI-based functional mapping. And we also saw the stimulation can elicit not only the phosphine from the subject, but also elicited a activation from the visual circuits as well as limbic structures of the brain. So a team of splendid researchers around the world, many of them are here in this audience, have made a great stance in innovations in this field. I would like to just go over briefly about some of the innovations that we have made as a community. So in terms of transducers, we have multi-array, single-element transducers, as well as hybrid approaches between the two. And obviously, the image guidance is very important. We have optical navigation as well as intraoperative MR guidance for doing it. In terms of acoustic coupling, people used water bath, some people used cone-shaped standoff, and we prefer to use a flexible hydrogel because it gives you more flexibility in moving around the single-element transducer around the subject's head. In terms of platform and size of the equipment, we have an integrated MR-guided FUS system, as well as cart-based system. Recently, we start to see portable devices that can be suitable for experimentation around the different species. In terms of simulation software to predict the acoustic propagation through the media, FDTD or FE can be adopted with semi-real-time computation algorithms. And imaging, the focus can be achieved by the technique called RV, acoustic radiation force imaging. This is one of the great interest field that can visualize invisible acoustic field in the brain. And we start to adopt multimodal integration of the technique. For instance, EEG, fMRI, PET is used for the evaluating the neuromodulatory effect, as well as we are utilizing the TMS and TDCS as a conjunctive therapy. So what we have learned so far, first one, both excitatory and suppressive effect can be achieved with slightly more studies that have been conducted on examining the suppressive effects. And FUS can also modulate the nerve function with potential application in examining the functional connectivity by sonicating the white matter tracks. The effects itself outlasts the sonication, so it has the potential in inducing the neuroplasticity. It first can also modulate the synaptic connectivity as well. So, and conjunctive applications with other brain stimulation modalities is possible, including fast-mediated BBB disruption. Also, we learned that repeated sonication can be given with promising safety profile, and fast neuromodulation is feasible in outpatient or medical office setting. And non-thermal and mechanical interactions are the main effector, although we still do not know exact mechanism behind it. And we have to note that the confounders, such as the auditory effect, may exist and call for cautions in designing and interpreting the results. So where are we going from here? First, in terms of first-line therapeutic uses, we believe, first one, modulating the level of consciousness is one candidate. For instance, UCLA group is performing this study. Of course, we can use the technique for target verification in HIFU surgery. And we can use it for ameliorating the major depressive disorder or PTSD or substance abuse. We can use the technique for epilepsy suppression, and perhaps we can use the technique for performance and cognitive enhancement. Of course, we have to make a steady improvement in techniques. People have thought about using the method of pulse modulation in terms of amplitude modulation as well as frequency modulation. We hope to achieve a better accuracy with tighter and steerable focus. We want to make the software runs faster and more accurate. And we want to improve the RF technique to gain the sensitivity to detect the low intensity ultrasound wave. Of course, we have to do more work on studying and understand the mechanism behind it. And all this effort should be made very carefully to validate its safety as well as to navigate through the regulatory environment. So I'd like to thank my funding agencies as well as collaborators to make this project possible. Thank you very much.